pronounced LFAM, by the way, not LFAM. But yeah.
I will tell you later why I stumbled, but I can't tell you in public.
That's not tell me in public. Okay. But yeah, hi, thank you everybody. My name is Louis. I'm here to talk about my research today, looking at digital twin frameworks for large format additive manufacturing, specifically a case study of LFAM for interior scale architectural elements. A bit about my background. I'm one of the younger students in the centre. I completed my Bachelor of Computational Design just last year. I'm an MPhil candidate here at ArchManu. My supervisors are Chris Bamborough and Nicole Gardner. Although I've only started my studies about 2 months ago, I've been with the centre for a lot longer than that, working as a research assistant for the better part of 2 years now, mainly working in our fabrication projects and different research projects that I've been working on the practical side mainly. These are some of the projects we've completed over the last 2 years. So last year we had our acoustic panels. We had printed a full set of acoustics for our office upstairs. We also had our mushroom project, which was looking at mycelium as a low emission building material. We just had a plywood floor. We had the mycelium panels, little 3D printed nodes, and then waffle cut cardboard structure that held it from behind. We also have bioshelter project, which involved 3D printing these molds. You use concrete to fill them up. All the concrete elements come together and they form an artificial reef that has been installed at the new Sydney Fish Market. Should be available for public viewing when it opens at the beginning of next year, I think. This year we've been working on FabPod, which you can see up to your left here. There's some Flintstone looking construction. Been looking at non-standard building materials with 3D printing nodes. Just a more general digital fabrication project of trying to use both organic and digitally fabricated elements. We have our Raffini chair, which there's a photo of on the next slide, which was a chair design done by one of our colleagues in Europe, and artist prints, just more general fabrication projects here and there of people coming in with ideas, and we're just working on them to try and fabricate with our robotic system. But working on these projects over the last 2 years has been very important for me because it's showed me how easily that small little delays or small errors can really turn into quite long deadlines or blowing out your cost quite easily. It's a process that you think you have mapped out, but you've just mapped it out manually, and then little errors or little foresights that you didn't quite see can really build up. And I know we talk about that a lot for mega projects, for all the big statistics that we throw around, but seeing it on a small scale in person has been really important for grounding this research for me. Here are some more of the specific large format additive manufacturing, essentially just a big 3D printer. These are our large format acoustic panels up on the left side of the screen here. We have our Raffini chair being printed in the middle there. We have one of our bioshelter panels up on the top right there, using fancy 45-degree slicing to try and overcome that overhang. And then we have a full example of the Raffini chair down the bottom as well. It's a very powerful platform. It's a very young platform. In Europe, there's been a bit more work into it. In Australia, it's been quite limited. But the way that we've been using this system is still quite dumb in terms of it's been trial and error. We've been calibrating manually. There's been lots of delays with lots of these projects, but it's been very important for us to understand that. But this is sort of the practical and hands-on approach that I'm looking to bring into my research. So going back onto large-scale projects, obviously these numbers have been talked a lot about today. The one I would like to focus on is the cost overrun for the budget forecast, 86%, and make a point that sometimes it's not necessarily the project becoming more expensive as it goes on. It's just a lack of understanding or an underestimation of that core of the project in the earliest instance. Sometimes we lack the ability to properly forecast out a project with all the different elements that can arise and not being able to see them as they come up. Different industries have different methods of approaching this, one being the example of a digital twin. Lots of people have been speaking about digital twins today, and the exact definition can vary between industries and contexts, but essentially it's made up of 3 main pillars, being the physical products or the physical system that you're trying to simulate, the virtual simulation of it in virtual space, and then the data that flows between those two things. And the data is the important part here because it means it's a dynamic relationship. It's not one thing being simulated linearly. It means they are living in harmony together and hopefully informing one another, so they're constantly growing. The integration of these technologies have been documented as quite an effective way to simulate and manage large, complicated systems. As they become more complicated, they help us build up an educated picture of the system to try and minimize or ideally eliminate the various mishaps that you get between the design of a product or a system and the operation of that. Or in a manufacturing context, the design of something and the fabrication of it. Lots of things can happen in that. Lots of errors can arise in that process. So being able to simulate it for the whole through can be very important. And then importantly, in an automotive setting as well, as I was talking about cost before, they can help us forecast cost, not just on a project timeline, but also moving forward through smart maintenance or being able to properly map out their life cycle past, using the materials past the life cycle and having a larger scope when you're analyzing the materials that go into it. But moving back to AEC, we obviously have BIM, which provide they're extremely data-rich models that provide a very, very good picture of how a building comes together and all the elements that go towards it. But it tends to be a static representation that won't always capture the dynamics of fabrication to try and bridge the design to the production of it. The fragmentation of the industry mainly that there's been talking about a lot today, where you have the architects will design, the construction people will do whatever they want, and there's not always a discourse between that. Digital fabrication is a way to try and approach this, more of a data-driven means of production, requires the precise, accurate design information to try and streamline that exchange between design and manufacturing. So CNC, 3D printing, all of these robotic means of fabrication are ways that we can try and improve that relationship. And additive manufacturing is a form of digital fabrication, and there's lots of industry and researchers that are actively looking into this as a way to reduce our material because it's additive, not subtractive. Manual labor, you're using the robot, you're not using manual processes, and then also a lesser energy consumption. I'm not very far into this project, but this sort of can tell the story of where I'm hoping my project will live, particularly looking at using large format additive manufacturing as a medium to try and explore some of these digital fabrication and digital twin concepts in architectural manufacturing. So you can see here, this is an example of one of the current software platforms using to simulate not just the robotic tool planning, but also the material and how it responds to different printing contexts. So that leads to my very early and fairly broad aim, but at the moment it's how can digital twin approaches from aerospace and automotive industries be adapted into architectural manufacturing workflows through large format additive manufacturing. The current progress, it's mainly just building on the experience I've had up until this point, printing, fabricating, and down at the lab we have down at the DFL. The lab itself has been printing for about 4 or 5 years, so a lot of what we'll be taking is practical experience that we've developed there. You've been using a range of materials across multiple life cycles as well. So not just taking virgin material, grinding it up and then discarding with it. You can take recycled material, you can print with it, grind it up, print with it again. And some of the elements that we have printed, even there's some in here, some down at the lab, have been printed up to 4 to 5 times while still retaining their performance qualities. Our case study will hopefully explore opportunities for synchronization, feedback loops, predictive optimization, but early days, so this is all ongoing. Because of the nature of needing to be responsive to the experiments that we're running, it'll be an action design research methodology that will obviously follow planning, prototyping, printing, reflecting, and ideally will be demonstrated through a full-scale example prototype of something interior elements printed with LFAM. And our technical workflows will engage with NVIDIA Omniverse for simulation. Adaxis is the screenshot I showed you before of the simulation of the robot printing. Rhino Grasshopper are always a good one-size-fits-all for lots of these tasks as well. So some combination of these softwares will be how we're trying to build a simulation workflow that covers not just fabrication, but also assembly, product lifecycle, and an appropriate pathway for product materials going forward past the initial use case, but being able to find, okay, this one's been printed, it has a certain amount of performance. Once we grind it out, we try and divert it to a next use case where its current material qualities is still able to be used in a different use case. Moving on to the anticipated outcomes at this early point will be a simulation framework for LFAM for built environment projects. The implication being that we can enable to avoid some of our inefficiencies and try and reduce our material waste. This framework will definitely grow as the technology is developing. The technology is very young. It's much more advanced in Europe, but still it hasn't been that long. So as it continues to develop for multi-material printing, our outcomes can be a lot more comprehensive rather than the mono-material examples that we have here right now, but could also be adapted for traditional manufacturing as it grows and becomes more comprehensive. It could contribute in future to material as a service ecosystems, right now probably limited to just staying within the large format additive framework, but eventually it could go broader and incorporate a lot more, as well as decentralized or direct to consumer fabrication processes. So that leads me on my call for collaboration of anyone in industry that has projects where they think there could be an applicable context to use a 3D printed element in a real life project or a real life building, and being able to watch and demonstrate and see how it lasts in particularly the Australian environment, having plastics outside, seeing how they last, seeing how they perform compared to more traditional forms. So I will leave you with some inspiration of what that could look like. These are some examples from a few companies in Europe as well. So lighting applications, interior wall paneling, furniture, parametric facades, things of that nature. If this spooks anyone's interest, I'd be very happy to talk further and see if there's any chance for collaboration. But thank you all so much for listening.
Thank you, Louis. Questions, please. Comments?
Actually not a question, just another tip. Have you checked out Branch Technology in the US?
No, I haven't.
They do large format 3D printed facade panels, freeform. So quite an interesting setup, and they went through the whole process in terms of durability, weather, fire, etc.
The Branch, you said?
Yes.
Okay. Thank you. I'll check it out.
Thank you. Shane, yeah.
Thank you very much. Beautiful eye candy with that. So this is very early for you, right? Do you already have a sense of the significance and the gap, say, even globally relative to what's going on in Europe and things? Are you beginning to sort of tease out from your literature and your searches what's the gap that needs to be addressed?
Yeah. It's sort of been two sides of myself fighting: the side that just enjoys printing and enjoys following the industry and seeing what advancements are made, and then trying to identify the academic gap. Most of it has been the lack thereof of specifically large format printing. Most people doing the advancements are companies, are private companies. So a lot of what they want, a lot of their techniques have not been published academically, especially not when talking about digital twins and simulations. So that is obviously ongoing, but right now it's been the lack of these combination of technologies, and seeing if we can find some potential workflows that bring them all under one roof.
Quick comment for me. You touched on it briefly, but don't underestimate the importance of the design for disassembly and circular economy principles being embedded in what you're doing, because that's going to be a key focus beyond just the beautiful shapes that we're making. What happens to them in the future?
Of course.
Just following on from that as well, like adaptive reuse, often when you're trying to put new materials in adaptive reuse, you've got to find ways to shape them in. Well, perhaps you've got an opportunity to use, we could do LiDAR scanning and a number of different things that you can actually be quite unique about your shapes to be able to kind of very carefully be accurately put in, and we'd see a lot of efficiency in both construction waste and installation.
Thank you.
Nice presentation, thank you. Talking to some of the people down in the DFL, one of the pain points seems to be interfacing Grasshopper to the robots.
Yeah.
Is that your target zone, or are you just going to hard basket? Or?
No, that's how we do all of the tool pathing that we do down there. We haven't ponied up and bought any of the commercial slicing options yet. So everything that we do is out of Grasshopper, which you have full control, but you're also completely responsible for everything. So how fast the material's coming out, how fast you're printing, how long you're giving each layer to set, like it's all completely manual. And all of the information that we put into it is stuff that we've learned ourselves. So I'm still not sure whether I'll be taking that on as part of it and whether I'll be getting really deep into the weeds or it'll be more of a big picture workflow, because obviously you can only focus on so much, but it's ongoing. But Grasshopper will definitely be a big part of it.
Hi, thank you for the presentation. It was a great set of prototypes. Specifically, you mentioned you produced acoustic panels, which captured my interest. What have you explored with those acoustic panels? Have you explored the materiality of it, the fabrication method? Have you tested any of those? Like, what's special about those acoustic panels?
Yeah, the main performative feature was there's micro perforations in the surface. So as we're printing along, we'll pause and then we'll move and then we'll continue printing and it'll produce a little hole. The idea was sound will travel through those perforations, get trapped between the wall. A hard thermoplastic like PETG is probably not the most acoustically suitable material, but that's the material that we've received through our streams. So it's more of a way to test our fabrication method. And yeah, I think we had some acoustic testing done. I don't know if we got the results back yet.
No, we had the testings done, but we haven't the results back. And but just from being in the room, the acoustics definitely have improved before, because we've been living in the meeting room for 18 months now. And I think it's definitely better. But yeah, the testings have been done. So we tested the room before, fabricated or did an optimization for the geometry, then fabricated with another kind of test. So we hope that the results will be published soon. So we submitted an abstract to Robertson Architecture. It's currently in the review. Yeah, coming over.
Thank you. That was a nice, very well done presentation again. So my question is, again, I'm from construction management, right? So my question may not be relevant to you, but I'm curious to know. So how does digital twin connect with additive manufacturing? Because digital twin is usually for existing buildings or projects. So are you bringing in like existing acoustics and then combining it with additive manufacturing, or how does that combine?
That's a great question. So it's more of a twin of the system. So you can be hooking up live sensors or a live camera that's monitoring the material output. And then if it's printing at a certain angle and it notices that there's an error, then that will feed back into the slicing software. And it might not save that specific model, but moving forward, it'll be informed in your design. If you have an overhang that's going too far, the system will know because of its experience that the overhang with that material in that context is too much. And so that's more of a simplified example, but more so how a twinning of the system is ideally informing the design process moving forward.
To give some context, for the last month or two, every 3D print we've done has been tracked with a camera of its printing output. So we've got now a huge data set of video data that explains, what kind of geometry was print and how the material came out, and if there was a drop or an overhang or any other kind of challenge that then can be used as a training set for improving the print. Other questions? Are you all desperate for coffee? We're desperate for coffee. Okay, then thank you, Louis.
Thank you.
Good, and we see each other.